Hello, everybody. Welcome to video 2 of lecture module 2, where we continue our story about protoplanets. And we are going to pick up with planetary differentiation. In the previous video, we talked about radioactivity, the way we are going to provide enough energy, enough heat to melt the protoplanets to allow differentiation to happen. So I'll bring up our slides and we will get rolling. So what do we have to talk about in this video? We are going to return to planetary differentiation. Let's actually differentiate our planets now that we understand the heat source is radioactivity from unstable isotopes. And then once we have that, we're going to have to talk about where do we get atmospheres? What kind of atmosphere? Do we inherit it from the solar nebula? Can we retain that atmosphere? Does a planet have enough gravity? Does it have enough mass to hold on to an atmosphere? So we have to talk about the types of atmospheres that we see and whether or not a planet can retain one. So we'll talk about mechanisms of atmospheric loss and atmospheric generation. And we'll round out. We should end by having a protoplanet, let's call it a proto-Earth, where we have a differentiated, a metal core, a high-density silicate mantle, low-density silicate crust, and then some form of an atmosphere that we could eventually turn into the air in this room that I'm breathing. So let's get started. So back to the accretionary process, back to differentiation. Remember that as we accrete all this material, it doesn't self-select, it just is all evenly mixed together, what we call homogeneously mixed, and some of that material is going to be radioactive isotopes that are going to radioactively decay, releasing energy, heating up material around them, causing the protoplanet to at least partially melt. So the protoplanet will heat up, start to partially melt, and once it gets molten enough, that's enough to let the dense materials sink to the center and the light materials to float to the top. So we'll end up in the center of our planet. We will have a metallic core, then a high density silicate, high density rocks, mantle, and a low density rock crust. This is what we should expect for every terrestrial planet, and a lot of the larger asteroids and larger terrestrial-like moons as well. So that is going to be the process of planetary differentiation. And remember that planetary differentiation is layering a planet according to its density. The most dense stuff, the densest stuff is in the center. The least dense stuff is at the surface. So I've tried to put together some pictures here so we can actually see this process play out and give you a visual you can put into your mind. So here I have a undifferentiated protoplanet, the end result of the accretionary era where we just put together the proto-Earth. Everything's nice and evenly mixed, and I've color-coded the different things in here. We have the dark gray metallic material, the dark green dense silicates, denser rocky material, the lighter, less dense brown silicate material, and then these angry looking radioactive elements and keeping them bright green in accordance to what I was doing in the previous video. All evenly mixed together. These are super radioactive elements. In fact, we're talking about the isotopes aluminum-26 and iron-60. Both have short half-lives, very, very rapidly decay from parent to daughter, releasing a lot of energy, cooking the protoplanet from inside out, allowing it to at least partially melt, if not completely melt. And then the dense materials, the metal bits, will start sinking towards the center. The middle density stuff, our high density silicate rocks, will settle in the central regions. And our least dense material, our low density rocks, will float to the top. Give that enough time and you'll end up with a differentiated protoplanet. Or really, at this point, we might not even want to call them protoplanets any longer. Sorry about that. Just a word to the wise. Try not to touch your face. I'm not doing so well with that one. But back to the video content. So here we have a high density metal core. Then we have a high density rock mantle, a low density rock crust. We have a differentiated protoplanet. We have done good work. And let's go ahead and review how we got here and add in a little bit of nuance to the story. So we start with a undifferentiated protoplanet. Everything's evenly mixed, and then the radioactive decay of unstable isotopes provides the heat that we need. But we need to get this heat, all this energy dumped into the protoplanet shortly after formation. We need a very radioactive element. And if you go back and see this in video 1, whenever I say very radioactive, what I'm really saying is radioactive elements with short half-lives. Short half-lives means that they are going to change from parent to daughter very, very quickly. They're going to give off lots of particle radiation and lots of energy, heating up the material around them, causing dumping in enough heat fast enough to melt these protoplanets. Well, let's think about this for just a second. So, our two players in this are going to be the radioactive isotope aluminum-26, which will decay, radioactive decay, to magnesium-26 with a half-life of 730,000 years. That's fast, by the way, for geologically. And then iron-60, which will decay to cobalt-60 with a half-life of 2.6 million years. It doesn't take too much hard thinking, like, wait, the Earth is 4.6 billion years old, and all that stuff was out in space for even longer. How do we get radioactive material into our protoplanets? There must be a source, and it must be a pretty recent source for when our solar nebula is forming. We have to inject radioactive materials into it. And if we want things like aluminum-26 that have very short half-lives, they better have been delivered right as our solar system was forming. Let's now add a bit more evidence. And it really points to, we can actually see in meteoritic evidence that we see the daughter products of these two things, so we know that they are the players. We can borrow from a little bit, if you're interested in Astronomy 152, I talk about how elements are created, and supernovae explosions are the only source that we know of that create aluminum-26 and iron-60. So this supplies evidence that what kicked off the collapse of our nebula, or after our nebula started to collapse, there had to be a nearby supernova, or nearby is a astronomically relative term, that created aluminum-26, probably kicked off our collapse, compressed the cloud, allowed nebular condensation theory to start, and also delivered aluminum-26 and iron-60. So you can start to see how interwoven and how well things are connecting. But we've done a pretty good job. We've been able to build a differentiated protoplanet. And again, let's think about proto-Earth. So we have our metallic core, we have our high-density silicate mantle, and our low-density silicate crust. So Earth is a pretty large planet. It's the largest of the terrestrial planets. We have a fair bit of gravity. We have enough mass. So as a terrestrial planet forms and as a gas giant core forms, they're going to have enough mass where they will have an atmosphere made out of the nebular gases that are hanging around. Our hydrogen and helium, the most prominent gases in the solar nebula, the most prominent gases and elements in the universe. So right after we form, we should expect our protoplanets, our proto-Earth, to have an initial atmosphere, a primary atmosphere as we call it, made of hydrogen and helium. Now, while the Earth is massive, it's not all that massive, so it doesn't have enough gravity to hold on to these light gases, which are moving pretty fast, so they will escape to space over a time scale of about 1 billion years, plus or minus a few. So we will lose our primary atmosphere for our terrestrial planets. It'll be a different story for the gas giants, and we'll come back to that. So if we lose our primary atmosphere, how are we losing it? What are the mechanisms? How is it lost? Why is it lost? Can we understand it? And will it be lost for the gas giants? This is an information-dense slide. I am aware, I've tried to color code it, and after this, I'm gonna have a summary slide that will hopefully get right to the points that you need to remember. So bear with me as I walk through how the terrestrial planets are going to lose their primary atmosphere. And in a bigger context, how planets lose atmosphere in general. And yes, planets are leaking atmosphere all the time. So why does the proto-Earth lose its primary atmosphere of hydrogen and helium? And for this, we have to consider a couple of things. Let's start actually down here at the bottom and start with a concept we have talked about before. So Earth has a set amount of mass, and that's going to dictate its escape speed. And what was escape speed? So going way back to when we were in person chatting. So let's imagine I want to get rid of this pencil. So I want to go, get out of here, pencil. I don't want you anymore. How fast would I have to throw this pencil? Well, given the mass of the Earth, I'd have to throw this pencil at a little over 11 kilometers per second. And then it would leave the Earth and never come back. So we have this concept of escape speed. Things that are moving at the escape speed or faster are lost and never come back. Now let's consider, how fast are gas particles moving? So how fast are the air particles moving in this room? Less than the escape velocity, or they would go to outer space and never come back, right? So what determines how fast a gas particle moves? The so-called gas velocity. And let's talk about the average speed of gas particles. Oh, wait, average speed of microscopic particles, average speed of gas particles? Again, going back to a concept we've talked about, that defines temperature. The average speed of particles, of microscopic particles, is how we define temperature. The higher the temperature, the faster the speed. The lower the temperature, the slower the speed. So let's now apply this to our protoplanets. The terrestrial planets are close to the sun. Temperatures are higher there. Things are hotter. Gases will be moving faster. As you get out towards where Jupiter and Saturn, and then where Uranus and Neptune are, it's colder and colder. On average, gas particles are going to be moving slower. We can already see it's harder for terrestrial planets to hold on to their gas, because if those gas speeds get to the escape velocity, then they're lost. And as we get to the gas giant region, it's colder, it's easier for them to hold on to it. What else determines the speed of the gas? So the other factor is, how massive is the gas particle you're talking about? How much mass does it have? Hydrogen is a very, very low mass. It's the lowest mass element, which means that it will be moving faster on average than a more massive gas particle like helium. Or it will be moving faster on average than say, two nitrogen atoms bonded together, which is the majority of the air in this room. So hydrogen and helium, being low mass elements, low mass gases per atom, will be moving faster. So what does this all mean? Let's put this all together, and you can see that right here. I've summarized it. No, you don't have to memorize these equations. So what is the average velocity of a gas? Well, it's directly proportional to the temperature. Higher temperature, faster moving. And it's inversely proportional to the mass. The more mass of the particle of gas, the slower on average it'll be moving. And this is the average speed, so some of them will be moving faster. So if we get our average speed close to the escape speed for a planet, we'll start getting more and more of those gas particles that are moving above the escape velocity of the planet. And if they're above the escape velocity of the planet, then if they go out to outer space, they're never coming back. They will drift away and go away. So when the average gas speed for whatever you're talking about, hydrogen or helium, gets to about a sixth or an eighth of the escape velocity, that gives you enough of the gas particles that are moving fast enough to escape and never come back, then you will lose an atmosphere on a timescale of about 1 billion years or so. So what does this mean? The hydrogen and helium of Earth's primary atmosphere is going to drift to space on a timescale of about 1 billion years or so. Earth just doesn't have enough mass to hold on to those gases at that temperature, so how fast they're moving for their temperature. I know, that was a lot. So let's break it down. Here is what I would like you to remember from the previous slide. So Earth is going to be too hot and not enough mass, as too low of gravity to keep a primary atmosphere. The same for all the prototerrestrials. So it cannot hang on to its primary atmosphere, the hydrogen and helium, that it inherited from the solar nebula, from its formation itself. And the factors you need to remember on whether or not a certain gas, hydrogen gas, helium gas, nitrogen gas, can be held onto a planet can hold on to it. So whether or not an atmosphere will be lost, the factors are the temperature of the gas, because that determines how fast the gas particles are moving. Hotter means that the gas particles are moving faster, which means that they're moving, more of them are moving above the escape velocity, and bye-bye. The mass of the particle, the more massive, the slower the average speed, the fewer particles that are moving above the escape velocity. It's easier to hold on to more massive particles. And then the escape speed of the planet. The more massive the planet, the easier time its gravity has holding on to the atmosphere. So those are the three factors that we have. And I want to go and show you how this might play out pictorially, at least for a proto-Earth, so an early Earth. So we start with a primary atmosphere, and what's in there? Mostly hydrogen, about 90% hydrogen. Don't need to remember those numbers. 9.9% helium, and about 0.1% more massive stuff. Just inherited from the solar nebula, this typical breakdown of the kind of gases that are in a solar nebula. I have here, you can see all the different gases in the primary atmosphere, and there's mostly hydrogen, there's less helium, and there's even fewer heavier stuff. This is the top of the atmosphere, so I will represent escape from the atmosphere if they can drift past it. So this is just after formation. We have a primary atmosphere, Earth being low mass, and the temperatures being pretty high. All of these particles, these ones are moving around really, really fast. These ones are moving around fast. These ones are not moving around very fast at all on average. So you give it a little bit of time, maybe a few hundred millions of years. Loss of the hydrogen has now escaped. A good bit of the helium has escaped. Maybe a little bit of the heavier stuff has escaped because we're constantly leaking atmosphere. Give that about 1 billion years or so, and all the hydrogen and helium will have escaped to space, leaving behind pretty much no atmosphere at all. Very, very thin atmosphere of the few gases that the Earth could hang on to. So we end up with a terrestrial planet without an atmosphere. No primary atmosphere is lost. Why is that? Because they're lower mass. They have less gravity. They can't hold on to it. They're closer to the sun, so they're higher temperatures, making the gases move faster on average, making it harder to hang on to those gases. So for every terrestrial planet and terrestrial-like body, shortly after formation, we really expect them to have to recreate a atmosphere, to bring in a new atmosphere. The second atmosphere this planet has had, our secondary atmosphere, because we're great at naming things. The gas giants, however, Jupiter and Saturn, they're very massive and they're farther away from the sun, so they're lower temperature. It's easy for them to hold on to gases compared to the terrestrial planets. In fact, they have enough gravity and they're cold enough where they can retain the hydrogen and helium that they inherited from the solar nebula. They retain their primary atmospheres and still have them to this day. So Jupiter and Saturn still have their primary atmospheres. It's mostly hydrogen and helium. Uranus and Neptune, they still have their primary atmospheres as well. Not as much, 1 or 2 Earth masses, as opposed to, say, about 300 for Jupiter, 1 to 2 Earth masses of hydrogen and helium. But it's still there, and they're very, very cold, and they have much more mass than the Earth, so they can retain their primary atmospheres. So in summary of what's going on with planetary atmospheres, we do not expect our terrestrials should lose their primary atmospheres. They'll escape to space. Our gas giants will still have their primary atmospheres. So how are we going to get the air in this room? Because I really do enjoy breathing. There is gas in this room. There is an atmosphere for the Earth. There's an atmosphere for Mars. There's an atmosphere for Venus. Not an atmosphere for Mercury or the Moon. Too small. Mercury is too hot, can't hold on to an atmosphere. Moon is too small, can't hold on to an atmosphere. So let's talk about how we're going to get an atmosphere on our terrestrial planets. Well, shortly after formation, after differentiation, that's a lot of heat. We melted an entire protoplanet, and there's still radioactive materials there heating things up. We still have radioactive materials providing heat in the interior of Earth to this day. But back then, there was more radioactive stuff. So these are still going to be quite hot. There's going to be a lot of molten material. And all of this liquid hot magma is going to want to go out to the surface. That means that early in their history, shortly after formation, all the terrestrial planets, all the terrestrial objects are going to have very, very violent periods of volcanism, spewing out this magma onto the surface. But not only is lava coming out of these things, but we're also volcanoes release lots of gases. They volcanically outgas. What kind of gases? The same kind of gases we see coming out of volcanoes today. What kind of gases are those? Carbon dioxide, sulfur dioxide, methane, ammonia compounds, water vapor are all being spewed out shortly after formation. And notice that these have things like oxygen, carbon, nitrogen, heavier elements, heavy enough for our proto-Earth and our proto-Venus and our proto-Mars to hang on to them. So we will volcanically outgas a second atmosphere, a so-called secondary atmosphere. And this atmosphere is going to be what we have to work with. So we can eventually, this does not seem like the air I'm breathing in this room. We're going to have to modify this to get to the air we breathe here today on Earth. But this is our starting point. We expect all the terrestrial worlds to end up with a secondary atmosphere that is made out of volcanic gases. So this is where I'm going to leave us. We have formed our protoplanets. We have reached the end of formation. We have differentiated protoplanets, and we have terrestrials with secondary atmospheres, and our protogas giants still hanging on to their primary atmospheres. We will pick up next time with the Earth. Thanks for tuning in, and see you in video 3.